Good morning. My name is Dawid KUKLISKI. I am PhD student at the Military University of Technology in Warsaw in Poland. I would like to present the research results presented in the article Index AI Metric of Training Time of Artificial Neural Networks on a Single Chip Computer. My presentation will be guided according to agenda in this slide. First, I will give you an introduction to the problem. Then I present the structure of the network used. Later, I will explain the term AI index and compare how different Z functions work to compute this index. Finally, let me then move to a last point, looking forward on the conclusions. There are many technologies for developing algorithms related to artificial neural networks. Solutions based on the cloud, computing clusters, or algorithms that use only the resources of the regular PC. Mobile devices also benefit from the neural network algorithms, but nevertheless, often these are services that use external resources. An interesting aspect is to test the capabilities of the single-board computer, such as Raspberry Pi, in confrontation with an algorithm using artificial neural networks. I would like to present an attempt to estimate the training time of convolutional neural networks on a single-board computers. Thanks to this, it will be easy to estimate the time needed to complete the learning process with much slower devices. The simplest solution to the considered problem of estimating learning time is to use the Python language, which is interpreted by many devices, and the Keras framework, a high-level overlay which simplifies access to many functionalities of the TensorFlow library. A Raspberry Pi has been used for the research as a single-board computer. This is a Raspberry Pi 4. Simply, convolutional networks were used to study the transferability of the structure for classification of the Canada MNIST dataset. This dataset is a large handwritten digit dataset consisting of 10 classes that contains 60,000 images for training and 10,000 handwritten digits for evaluation. Now I am putting up structure of artificial neural network used. Each convolutional layer had neurons with ReLU activation function. The structure of CNN version 1 consisted of exactly 32 neurons in the first layer and 64 neurons in the second layer. On the other hand, the CNN version 2 structure consists of 32, 32, and 64 neurons. The first step was to compare the speed of network learning on different devices. The networks have been trained on the set consisting of 60,000 samples. Notice that a single-board computer is much slower than a desktop computer. The learning time of the digit recognition network by the computer was 167 seconds for the two conventional layers and 200 seconds for 3 layers. Notice that the single-board computer is 17 times slower than a desktop computer. Using a fairly popular Keras framework for Python, it is possible to transfer previously designed precompiled neural network structures from one device to another. The test was performed based on 10,000 samples. The tests were carried out as follows. In the first step, the identical network structure with the same initial weights was trained with the same algorithm on Raspberry Pi and on a desktop computer. After the training process, the operation of the algorithm trained with a single board computer was tested on it. Then, the structure saved in the file, trained on a PC relay, was transferred to the Raspberry Pi and tested on the same dataset. Based on the collected data, you can try to create an estimation of the time needed to achieve the assumed accuracy in relation of the time of learning on a desktop computer. This is the slope factor of the curve depending on the complexity of the structure of the artificial neural network and the hardware capabilities of the device on which the algorithm is to operate. This is the proposed index IE. In the other words, is the ratio of the training time of one epoch on the desktop computer to the training time of one epoch on the single board computer, where P is number of algorithm training epoch, W is number of layers, K is scaling factor, and T is training time of given epoch on reference computer. But how looks like Z function? During research on Z function, the effects of many different functions were compared. The best one is this, and looks like this, where P is number of epochs, W is number of layers. The comparison was carried out by applying the Pearson correlation function between the AI index calculated on the basis of measurements during the test and the proposed index calculating using successive functions. The best score is for this one. Based on the conducted research, the correlation between Z and A is 99.92%, which is promising result for finding a apparatus for the estimated training time of artificial neural networks on devices such as Raspberry Pi. What about K-factor? Work is currently underway to establish the K-factor for normalized Z function. Thanks to this, it will be possible to estimate network training time on less efficient platforms. What is more, there is no limit to use the same framework on different computing platforms. A previously trained network can be used on a single standalone device without need to use external services. The dynamically developing research of artificial neural networks requires a quality measure estimating the hardware capabilities of device for complex networks to predict the time needed to train the neural network algorithm. Thank you for your attention. If you have any questions, feel free to write to us.